A table of values. So what's the answer to your question?
So it's okay to use a calculator.
It's the only way to do this.
Well, I didn't know,
Okay,
like-
you're doing this around 1. If you plug in like 1.01, to do 1.01 to the 10th power, what would you need to do? 1.1 times 1.1 times 1.1 times 1.1 times 1.1 many more times, and then you'd make a mistake, and then you'd get sad because you just wasted some of your life doing something that you shouldn't have done. This is exactly why you have calculators, because you can't do this one by hand in any reasonable amount of time at all, period. So, what do you need to do? Oh, look! Wait a minute. It's amazing. It's already in the calculator. Cool. Amazing. It's amazing how that happens. What function on your calculator do you hit next? Let's go to table set. Oh, round 1. Oh, it's amazing. We're already starting at 0.997, and the step is 0.001, and we hit graph. Oh, look at that! Amazing. It's already there. Okay, so here's our table of values. What does this table of values strongly suggest? What does this table of values strongly suggest?
That the limit is 6.
It looks like the limit is what? It really looks like it's 0.6, especially since if you get two values around the error right there, you average the two of them, and it averages out to 0.6 exactly. Yes, done. And if you when they say use a graphing utility, they want you to actually graph the function. So theoretically, you could graph this function. What's the hardest part about graphing this function? It is not typing it in. What's the hardest part about graphing this function? What? Finding the window that actually makes sense and gives you something useful, right? Now, we have an idea that the limit is about 0.6, right? So we want to stay around 0.6. So if we set the window, our x-min, let's say, I don't know, 0.4, and our x-max is, I don't know, quit. Let's go to window. It's like the y-min 0.5, make this 0.7. The tricky thing, though, is we need to know what our x values are, right? Well, we kind of know already because we're taking the limit as it goes to 1. So let's say, I don't know, 0.1 to 1.1. We could theoretically be zoomed too far out still, right? If we graph this, what's it look like? That's kind of cool. What do you actually notice in the middle there?
There's an empty space.
It actually has the space, which is actually pretty cool. It'd be neat if they added some sort of a little tiny bit of programming to actually draw a dot, but they don't. So this actually matches pretty nice. You would say this by saying this. What's the limit as x goes to 1 from the right of this function? What's the limit as x goes to 1 from the right? 0. But what's the limit as x goes to 1 from the left?
1.
Yeah, they're not the same, so the limit doesn't exist at. So then you say the limit as x goes to 1 of f of x what? Does not exist. Exactly. The same thing is here, right? The same thing, except the values are a little different. What's the left-hand limit at x equals -1? The left-hand limit is 3, and the right-hand limit is -1. They're not equal, so does the limit exist? No.
Nope.
That's all they want you to ask. That's all they're asking you for. Because everywhere else the function is continuous, so the limit exists. Instead, we could just make the table. What's the limit approaching? We're trying to go to 0 from the right, correct? If we go to 0 from the right, for our table set, what should we start at? Negative what? What do you want to start? Negative point what? This is our starting value. We want to get a path. This is not our step. Let's not get too close. So how about negative, I don't know, 0.5? What should our step be?
0.01.
Let's make it 0.01, right. Oh, and we're supposed to go from the right. I'm sorry. So what should we start at? But can the delta be negative? Do you know? Do you understand what I'm saying? Can the delta be negative? I mean, logically it can. Let's just try it. Let's start at 0.5, and let's make it negative 0.01 and see what happens. You sure can. Look what it's doing. Look, do you see how the table's counting down right there? Cool. I didn't realize you could do that. So are we approaching from the right? We're approaching 0 from the right, correct? Okay, is it going berserk? Doesn't look like it's going berserk.
It's going steady.
It's nice. It's pretty good.
I feel like it's going to go on a minute.
Yeah, so let's do this here. We keep going down. And it's not defined. That's why we can't do it. But what does it look like it's approaching? Really?
Negative 0.5. It's 0.005 is what I got.
What does it look like it's really? Oh, well, you guys did even closer, right? Judging by these numbers, the smallest one is negative 0.046, right? But maybe we need to get closer. So if we wanted to get closer, we just need to change our table view, right? Instead of starting at 0.05, let's start at 0.001. And what should our step be? Negative 0.0001, right? We're running the risk of, well, it's actually pretty good. We want to go to 0, right? Look at this. Oh, wow. What is that number? Negative 9 times 10 to the negative 4th. That's really small, right?
0.00009.
Exactly. So maybe what should we do again? Change the table view again. We just got closer, but maybe we should get even closer to see if we can. The problem is the calculator's kind of limited, right? We can't go too far in or it starts rounding. So let's try it one more time. Let's make it 0.0001, 0.12341. So is this correct? I think. Here's the table. Are we really close to 0? Yeah. As we get closer to 0 here. Oh, we needed to make it negative, didn't I? I didn't make it negative. Negative 0.1234. Now it's going down. You see how it was going up before? The x should be going to what? 0. Are we getting closer and closer to what?
0.
It really looks like. So based on this right here, what do we think the limit is?
0.
Really think the limit is 0. It really seems like the limit is 0. Now, here's the thing. Do you have a way of proving it's 0?
No.
Not yet. It really looks like this is very, 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 very small. So we think that this limit is going to 0. Can you prove this yet? No, you really can't. But just because it goes to something close to 0, does it necessarily mean it has to be going to 0? No, but we just zoomed in again and again, and did it keep on getting closer to 0? Yeah, so we're pretty sure it's going to 0. Pretty sure. You can take it out, exactly. You can take C and you can just bring it out. That can be helpful because sometimes you don't have to multiply by a big number when you're taking the limit. This is supposed to be a multiplication sign right there. That's a multiplication sign. So if you have the limit of the product of two things, you can just do the product of the limits. And this one's pretty straightforward. You can do the limit of a fraction by doing the top and then the bottom as long as what is true. The bottom can't be 0 because we don't like dividing by 0. We do not like dividing by 0. So none of these are meant to be earth-shattering. If we look at the next set, they look a little more complicated, but again, one of them is almost a total repeat of another, and they're not meant to be super, 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 super disgustingly complicated. You have the limit of something raised to the nth power right there. What can you do instead? You can do the limit and then do what? Do the power afterwards. That is very helpful sometimes. The limit of a constant is always if a function is always 5, the limit is always going to be 5. Can you approach anything else? No. The limit of y equals x is always the a value if you're approaching a, because when x is 5, what's y? 5. When x is 6, what's x? What's y? 6. It's always the same thing. For number 9, what's the first thing you always check when you're evaluating a limit? You always check to see if you can do what? Yeah, can you plug in a into that? Yes. So what is x to the n? The limit as x goes to a? It's a to the n. And number 11, we'll skip over 10 for a second, is identical to 6 because when you're doing the nth root of something, that's equal to what, question mark, to what power?
1 over n.
1 over n. Square root is to the what power? Cube root? Fourth root? Nth root? 1 over 5th? Nth root is 1/nth power, okay? 1 over n. Now for this one, it's very similar. It's just a corollary, or sorry, a result of 11. So these are ways in which you can attack limits. These are ways in which you can attack. Where does g of x live? Someone tell me very clearly where g of x lives. Where does g of x live? Between f of x and h of x. Can g of x ever be greater than h of x? No. Can g of x ever be less than f of x?
No.
Can it be equal to them? Sure. Can it be equal to them at the same time?
Yes.
Yes. But can it ever go outside of them?
No.
Can h of x ever be less than f of x?
No.
Can f of x ever be greater than h of x? No. So graphically, this is what it looks like. Let's say the ceiling function is h. Here's h of x. Let's say we have our floor function, which is g. Here's g of x. at this x equals a value, we're going to say that this is y equals L. So what's the limit as h go? Sorry, not h. What's the limit as x goes to a of h of x? Yeah. What's the limit as x goes to a of g of x? What the squeeze theorem tells us if and what I'm going to add to this is, let's say, remember this was f, I'm sorry. I want to keep the notation consistent. This is f. G always lives between them. So there it is. There's g of x. So g of x is always between it. So therefore, what do you now know? By the squeeze theorem, what do you know? The limit as x goes to a of must be what? Is there any way for it not to be L? No, it has to be, because it's totally sandwiched between those things. And we've just figured out that those functions press it together at a to L. The question is, why is this useful? Seems pretty complicated, right? Like, it seems pretty specialized. And you're right, it is specialized. If you said that, you would be totally right. Here's where it comes into play. Sometimes functions, finding the exact limit is very hard, but it's really easy to find a function that's always greater than it, and it's sometimes easy to find a function that's always less than it, that you can sandwich it between. Is this something you're always going to be able to use? No. In the beginning, you're going to get questions that say, use the squeeze theorem to prove that this is true. And then it's going to say, can you use the squeeze theorem? And then eventually you'll be able to recognize certain things that scream, use the squeeze theorem. Here's one example. If I gave you this, the limit as x goes to 0 of x squared sine x, can you plug in 0? You can? What sine is 0? What's x squared when x is 0? Yeah, absolutely. You absolutely can. So you can just actually do that out and think, hey, you can plug in 0. You're done. What does this look like graphically, though? If you graph this function, it looks like this. And I'm going to draw it kind of messily. Like this. Is that okay? Yep. Okay. And it will cross at 0. I'm going to change this. Oh, no, we'll do it this way. We'll do this one first and then do the more complicated one. That's fine. Can you tell me, here's another way to prove it without just plugging it in. Sine of x, what is that always less than? Always. 1. What's it always greater than?
0.
No. -1, right? Do you agree that that's always true? I agree that that's always true. Okay, so if you have any sort of algebraic equality or inequality, as long as you don't multiply by a negative, can I multiply through by the same thing and it doesn't change anything? So for example, could I multiply everything by 6? Yeah, sure. Can I multiply everything by 7? Is x squared positive or negative? Positive. Squaring anything is always positive, right? So I'm going to multiply everything by x squared, and you get negative x squared is less than or equal to x squared sine x is less than or equal to? Okay. What's the limit as x goes to 0 of negative x squared? It's not a trick question.
0.
What's the limit as x goes to 0 of x squared?
0.
Therefore, that's what the 3 dots mean. What's the limit as x goes to 0 of x squared sine x?
0.
Because it's stuck between the two, right? Exactly. So by the squeeze theorem, that has to be true. We've proven it. But here's the thing. We could have just evaluated it, right? You could plug in 0 and we're done. So let's make it slightly different. Let's say I gave you this. X squared sine of 1 over x. Can you plug in 0?
No.
No, you can't. You can't plug in 0. You can't. Do you agree with that?
Yes.
Okay. Sine of 1 over x. What's the biggest that can possibly ever be? It can never be greater than 1, right? What's the smallest it can ever be?
-1.
Let's multiply by x squared. You can, but we're not doing the estimation. We're doing the let's prove it, okay? We're not making a table in this case, Hunter. So do you agree that that's true? Do you agree? Is that true? It has to be true, right? Can you tell me what limit as x goes to 0 of negative x squared? 0. It's the limit as x goes to 0 of x squared. 0. Therefore, by the squeeze theorem, SQT, what do you know has to be true? The limit as x goes to 0 of 1 over x has to be
0.
And that's a proof. It is 0. Could you get an idea that it's 0 by looking at the table? Yeah, but if you zoom in really far, for example, if you zoom in on this, sine of 1 over x, we zoomed in on that before. We looked at that before. We looked at that function, I think, or something. Pi over x. It's the same thing visually. As you keep on zooming in, what happens? It keeps on oscillating, right? So does it ever approach? No, it's just going. It's ballistically going back and forth, right? But what happens? So, for example, what's the limit as x goes to 0 of 1 over x? It doesn't exist because it's going berserk around the origin, right? But by adding that x squared to the front, what happens? It forces it to go to what? 0. It forces it to go to 0. So here's the key. In the beginning, when you use the squeeze theorem, you're going to be told, use the squeeze theorem, okay? Then you're going to have to recognize when you should use it. What types of functions are usually going to be present when you use the squeeze theorem? Trig functions. Because they're naturally bounded. Sine and cosine max out at 1 and they min out at what? -1. So they're already stuck between two things. You will need to build the functions, but trig, when you see sine or cosine and you see a limit, you want to automatically think to yourself, maybe I can use the squeeze theorem. The squeeze theorem can come into play in other places, but for the most part, it won't. And at the beginning, you're going to be told, use the squeeze theorem.